11?
It was lecture 1. Oh, okay. I'm thinking lecture 2 of induction. Sorry.
No.
That's 11. My bad.
Okay, tonight we're going to talk about recursion and induction. So we're going to start out with some examples of recursion. And we're going to find the closed form for some of them. We're going to do it vice versa. We're going to start with some closed forms also and find some recursive definitions. And then we're going to figure out some methods for figuring out closed form from recursions, and then how to prove them by induction. So it's going to be lots of fun tonight. So let's remember first what the definition of recursion is. So what are the elements of a recursive definition? If I define a function recursively, I have to have two parts, right? I have to have a basis, and I have to have a what? A recursive step, or a recursive rule, or a recursive definition, any of those. So these are the two parts that I have to have for any recursion. So if I only have one of them, I have an incomplete definition for a recursive sequence. So let's start out with some examples. Here's an example. There's my basis, f of 0 equals 1, and f of x equals 2f of x. So when you want to understand how a recursion works, it's really good to make a table of what the values are for that recursion. So if we want to figure out what this function does, we might make a table of x values and f of x and find out what those values are so we can get a feel for what the values are going to turn out to be. So when x is equal to 0, we use the basis to find that f of x is 1. If you remember the way we wrote the code for recursion last time, we had an if statement. When we did a function definition in our recursion, this would be function f, and x would be our input. And we'd say if x equals 0, return 1, right? And then else return 2 times f of x minus 1. Sorry, that should be a minus 1 there. So we should have a minus 1 in our formula for f of x. And that was our code for our function. So our basis is, first we check for whether x is 0 or not, and then we find f of x if it is. So then when x equals 1, that's twice the previous value, so that's 2 times 1. When x equals 2, it's twice the previous value, which means that f is 4. When x is 3, f of x is 8. So this is going to be powers of 2, right? So we think the next value is going to be what? 16. So if we wanted to guess at a closed form, the very first way of guessing at closed form is to make a table and make a guess from what you see. I see powers of 2 in this table. And this is 2 to the third. So the nice thing is the power is the same as x. So I think f of x is going to be equal to 2 to the x. How do you think this formula might change if f of 0 was a different number?
It would just start off at a different basis.
It would have a different basis. So let's try another one just like this with a different starting point. So after we guessed this closed form, we could prove it by induction. But we did the same proof, I believe, last time. So we're going to do some other examples and prove them by induction instead. So let's try a different example where we have another starting point. If we say f of 0 is equal to 3 maybe, and f of x is twice the previous value, then if we make our table of x and f of x, let's see how that changes from what we had before. And the first value is 3. Now the second value is twice that, so it's going to be 6. Twice that's going to be 12, and then 24. And then twice that is 48 and 96. So what would you guess for the closed form for this?
3 to the x.
3 times 2 to the n.
These are 3 times powers of 2, right? So this is 3 times 1. This is 3 times 2, 3 times 4, 3 times 8, 3 times 16, and 3 times 32, which are powers of 2. So this is equal to 3 times 2 to the 0, 3 times 2 to the 1, 3 times 2 squared, and so on. So we're going to guess that the closed form is f of x is equal to 3 times 2 to the x. So you might not always be quick in this, but you notice that whenever we have, this is called a linear homogeneous form, where f of x is dependent only on previous values of f, and it's multiplied by a constant. So it doesn't have like a plus 1 out here or something else. This is called homogeneous, if we don't have any terms that look different. So we just have f's and numbers in front of them. That's a homogeneous function there. And when we have that kind, we know we're going to have some power in the closed form. So we're going to do some more complicated examples of those where we're going to find the power that we need to know, what number is going to be raised to the x for the closed form. Are there questions on this? So eventually you'll be able to look at some of these and be able to tell sometimes what it's going to be like. So here I already knew it was going to be 3 times 2 to the x instead, because I was just multiplying the first term by 3. And it didn't do anything in this step. I didn't change this step at all. So it just multiplied all of them by 3 instead of changing the formula. Okay, let's try some more examples where we make tables and guess the values. Let's say f of 0 equals 10, and f of x is equal to f of x minus 1 plus 3. It's always good to look at about 5 values. If you look at just 3 values or 2 values, you might not get a really good sense of what the pattern is. You might see a pattern that's not there. And even just for 5 values, you might see a pattern that isn't there, or that doesn't play out in the rest of the sequence. So our first value is 10, then we add 3 to that, because we take the previous value and add 3. And then we have 13, 16, 19, 22, 25. So is anybody going to hazard a guess on this one?
10 plus 3x.
That might be a good one. So 10 plus 3x would be here, 10 plus 3 times 0, 10 plus 3 times 1, 10 plus 3 times 2. Looks pretty good. So that does look good, and it makes sense because each time we added 3 for all of the x values. Starting with 1, we added 3. So the formula for this one is going to be f of x equals 10 plus 3x. Okay, let's do another example. Let's see, let's try so here's a more complicated example where we look back 2 for the recursive step instead of just looking back to the previous value. So let's make a table for that and see how that works. It never ever hurts to make a table, by the way. Just so you can double check your thinking about what's happening in the sequence. Okay, we say that f of 0 is equal to 5, and why did I also define f of 1?
You gotta look back 2 steps.
If I have to look back 2, then I can't determine f of 1 from just knowing f of 0. So I need to define also f of 1, but f of 2, I can look back 2 and find out what that one is. So this number here determines how many things are in my basis. I have to have at least 2 things in the basis. It doesn't hurt to have extra things in your basis. So f of 1 is equal to 0. Now we use our formula. So f of 2 is now going to look back to f of 0 and add 3 to it. So that's going to be 8. The third one's going to look back to 0 and add 3 to that. So we'll repeat that process. So 8's going to add 3 to get the fourth one. And we're going to add 3 to 3 to get the fifth one, and so on. I may or may not be able to derive a formula for this right now. But I'm going to teach you a cheat method for deriving the formula if you can't guess it from the table. Actually, not for the formula. That's a cheat method for something else, so I'll do that in a minute. Usually, when you're looking at a table and you're trying to find a closed form, a lot of what you might do is look at consecutive values and see what the difference is going to be. So the difference here is if I take this and subtract that one, that's minus 5, and this minus this is 8. And then this minus this is minus 5, and then 8. F of x minus 1 minus 5. Right. I have a feeling on this one you'd have to use a power of minus 1, actually, to get you to subtract the right things on the even terms, and on the odd terms to do something else. But this is just practice in making this table, so I'm not going to try to do closed form because I'll probably just make you confused. But I'll do some examples like this next time with some closed form from the table here. But I'm not going to make you guess any that are really hard on your homework. So there's ways that you can guess things, and there's also ways that you can figure out for sure what a closed form for a sequence is, but if it's in the right form. This is not in the right form. This is not homogeneous because it has a plus 3. So if all the terms had f's, then there would be a formula for me to do this, which I'm going to teach you in just a little bit. So we're going to do a couple more examples first. So we've got some examples of just looking at recursions and making a table for them, and sometimes making a guess at what the closed form is. So I can't always make a guess. Like from that last table, I probably wouldn't have made a guess. So let's try another example. So our basis is given, it's 5. Our recursive step tells me to look back to the previous one, multiply it by 2, and then subtract 1. So then my next one's going to be 17. 17 times 2 is 34. Subtract 1, that'll be 33. The next one will be twice that minus 1, so that'll be 65. And then that'll be twice that minus 1. It's going to be 129. This looks close to powers of 2 to me. Looks kind of like 4 plus 1, 8 plus 1, 16 plus 1, 32 plus 1. Yeah? So that's equal to 2 squared plus 1, 2 cubed plus 1, 2 to the 4th plus 1, 2 to the 5th plus 1. And this should make some sense because I've got a 2 times f of x, so a power of 2 being in there makes some sense for this. So in this case, the power is 2 higher than the x value. So what do you think the formula is going to be?
2x. 2 to the x plus 2.
2 to the power x plus 2, and then add 1 to that. Now, the less sure you are of your closed form, the more likely it is that you need to do an induction proof to prove that the formula you came up with goes with it. So there's a theorem in mathematics that says that there's an infinite number of sequence definitions that can describe a sequence of 5 numbers. So there's lots of possibilities for closed forms for sequences. So when you guess one, you need to go back and prove it if you really want to use it and be sure that that's true. So you need to prove it by induction and be sure that it'll be true infinitely and not just for the 5 cases that you just looked at. Now, in this case, I'm pretty sure because this is pretty simple. But in general, you want to use induction to prove that recursive closed forms are true. So let's just do this one right quick. And in induction, we have to have the same kind of parts that a recursion has, right? We have to have a basis and inductive step. And we have to use something that we assumed to get a previous one. That's just how recursion works, right? We have to have a basis, and we have to use current values to get new values, and that's the same way that induction works. So induction and recursion sort of go together. So let's prove our closed form, which we said was f of x, I can't write up there, is 2 to the x plus 2 plus 1. And our basis, so we have a recursion on the left and a closed form on the right. Anytime you need to prove that a closed form is correct for a recursive definition, it doesn't matter if you start with the closed form and end up with a recursion, or if you start with a recursion and end up with a closed form, you'll do the induction in the same way. So for the basis, f of 0 equals 5 comes from the recursive definition, and from the closed form definition, that's equal to 2 to the 2 plus 1, which is equal to 5, and I would check that off for being true, because both of these are equal. I have my assumed step. So I assume that f of x is equal to 2 to the x plus 2 plus 1. I write my closed form in my assumed statement. In my proof statement, I prove f of x plus 1's closed form is going to work. So that's going to be 2 to the x plus 3 quantity plus 1. That will be what I'm going to prove in this induction. So this is my setup, and that's all complete, and I have 60% of my problem done so far. Now, in a recursive proof, in a recursive induction proof, what you start out with is the recursive definition. So I start with my left-hand side of my proof statement, f of x plus 1. That's normal, right? We usually start with the left-hand side of my proof statement. But we can't set it equal to that. We need to use our recursive definition to get our left-hand side in terms of what we assumed. So f of x plus 1 is going to be equal to what?
X minus 1 minus 1.
X. X.
Alternatively, in induction, you can also assume for x minus 1 and prove for x. It doesn't matter what you do. As long as they're 2 consecutive values, that'll work just fine. So we're using our recursive definition for f of x plus 1. So this is sort of a given too. Our recursive definition is given, and our assumed statement is given. Those two things are given. We're going to use them together to get the right-hand side of what we're proving. So now we have to use the assumed statement for the f of x term here. So what do I do now?
Substitute x plus 1 for x.
I'm going to use this statement, so I need to do a substitution from the assumed statement for f of x. Because I started with this, I started with the left-hand side of my proof statement, my goal is to get this. So in order to get there, I need to use this. I need to use the right-hand side of my assumed statement. So I'm going to do a substitution into the recursive definition. So instead of f of x, I'll put what? 2 to the x plus 2 quantity plus 1. And then I'll subtract 1 from that quantity. And then I'm going to do some algebra until it looks like the right-hand side of my proof statement. So the next thing is I'll multiply this 2 out. So I get 2 times 2 to the x plus 2, plus 2, and then minus 1. And 2 times 2 to the x plus 2, I add powers, right? 2 is 2 to the 1, so when I add those powers, I get 2 to the x plus 3, which is looking good because that's part of what we wanted to prove. And then, what do I get next? This 2 and minus 1 gets adding plus 1, and that is exactly what I wanted to prove. So I'm going to review what we just did. If we go back and look at our proof, we do our basis first, starting with the definition from the recursion, and then we show from the closed form that that's equal. So we're assuming that the recursive definition is true, or proving that the closed form is true. So in our assume statement, we assume that the closed form works at one point and hope that it works for the next point. So in our proof statement, we prove it for x plus 1. The very first step of our proof is to use the recursive definition, because that helps us write the proof statement in terms of the assume statement. Because the recursive definition, by definition, defines f of x plus 1 in terms of f of x. So it's very convenient that our recursion works that way. So that's the first step. The next step is substitution from the assume statement, and then we do algebra until we get our right-hand side to look correct. So let me write down that sequence of steps so you have it. So even if you knew the closed form first and you derive the recursive form, an inductive proof is an equals proof, right? So we're proving an equals. So it doesn't matter if we assume one side and show that the other side is equal, or if we assume the other side and show that, if we reverse it and show the other one's equal. Once we've shown that they're equal, it didn't matter which one you started with. So it's easier to always do your proofs the same way. So we assume that the recursive step works, and we prove the closed form works even if we started with the other one. So we assume that the recursive definition is true. And we prove the closed form. So that tells me how I have to write my proof. So then I do a basis, and I show that the recursive definition and the closed form give the same value. Then in my assume step, I write the closed form. And in the proof, write, and this is for x. Actually, we can just say for x minus 1 and write the closed form for x. Or any two consecutive values is fine. Whichever is easier for you. You can start with x minus 1 and go to x, or you can start with x and go to x plus 1. And then after you've done the proof statement, you start with f of x equals, and then you use the recursive definition, right? And then we substitute the assume right-hand side into that recursive definition. And the final step is just to do the algebra until we get the right-hand side of what we're trying to prove. Okay, we'll do some more examples of this, so we're going to make this more concrete before you leave today, so that when you're doing your own, you'll have a natural feel for what you have to do next. So I'm giving you lots of formulas for doing proofs, because these are ways that people do them and that everybody understands that that's how the proof works. It's not that other methods aren't valid, it's just that this is an accepted method and it works, and it's not very hard. So if you're going to try something else, you're going to have to be more creative in making sure that you've covered all the bases. So induction is an accepted method of proof, and these steps that I'm showing you will help you do it the right way all the time. Okay, so let's find some, I'll give you some examples of closed form, and we're going to find some recursions for those. So here's a function definition. F of x is equal to x. So we can find, so we're going to go from closed to recursive. And again, making a table can really help. So let's try that here. This is a really simple one, right? If f of x is equal to x, both of these sides look the same in this table. So now if I want to figure out what f of x is in terms of the previous one, what do I have to do to the previous one?
Add 1.
So f of x is equal to f of x minus 1, and then what do I do to it?
Plus 1.
So going from here to here means I add 1. So that's a good recursive step, and we also need a basis. So we can write f of 0 equals 0. And since I did my recursive definition just looking back 1, I know I only need one element in my basis. If for some strange reason I said that f of x was equal to another recursive step that would work would be f of x minus 2 plus 2, right? And then I would have to have how many elements in my basis? I'd have to have 2. I'd have to say what f of 0 was and f of 1 was. So another way, so when we're looking at a closed form and trying to find a recursive sequence, we're going to do the same thing. We'll make a table and see how consecutive values change. So I'll do a few more examples. That was a little bit trivial, so let's do some other ones. So if we have f of x is equal to 2x plus 3, let's try that out. Make a table. So f of x is going to start out being 3. Then it'll be twice that plus 3, which is going to be 8. Twice that is 16 plus 3 is going to be 19. Twice that is 38 plus 3 is going to be 41. Twice that's 82 plus 3 is going to be 85. So if I want to find the difference between consecutive values, I probably need to make a little table of the difference. So the difference here is 5. The difference there is...
It shouldn't be.
Sorry.
5.
Oh, I messed up my whole table, didn't I? Okay, so f of x starts out at 3. And then it's going to be, 2 times 2 plus 3. I was acting like this was a recursive definition. Let's just make a new piece of paper. I don't want you guys to get too confused with what I'm writing up here. How come it takes you so long to tell me I made a mistake? You guys just believe everything I say, don't
I
you?
think you're too fast, so we are lagging in
You're right,
catching
pretty
up.
fast.
You're pretty fast.
Yeah, blame us.
That's right. That's all your fault. Okay, so this is 2 times 0 plus 3, which is going to be 3. 2 times 1 plus 3. I was totally doing recursive definition. Okay, so 2 times 1 is 2 plus 3 is 5. 2 times 2 is 4 plus 3 is 7. 2 times 3 is 6 plus 3 is 9. 2 times 4 is 8 plus 3 is 11. Now, y'all remember my mistake story, right? I'm supposed to make mistakes so that you can figure out how to fix your own.
It's some story you got there.
That's right. It's a good story.
2.
Whoa. That's nice. All our consecutive differences are the same. We should expect it since it's a linear closed form, right? So we think that f of x is going to be f of x minus 1 plus 2. And we need a basis. F of 0 equals 3. And if we look at that, that should remind us of the function we had before. If we had a recursion that looked like plus 2, we were going to add like plus 2x was going to be one of our terms, and then the basis was the other term. Okay, let's do another one. And this one, I will introduce you to the cheap method of finding a recursive sequence. I call it the cheap method because you don't actually have to look at the table to find it, but we'll make a table just to make a table, because we should. Pattern finding is really a good skill to have. As a matter of fact, a lot of research areas have to do with teaching computers how to find patterns in things. And the more practice you get in finding patterns, the better. So if you make a table and you start seeing powers of 2, you start seeing, n squared or something in there, it's a good development skill for you to find patterns in numbers. So no more recursive definition here. It's a closed form. So this is 1 plus 1 is 2. 2 squared is 4 plus 1 is 5. That'll be 10. 4 squared is 16. So that'll be 17, 26, and 37. So we can find the differences. And we can guess closed form from that. Sorry, we can guess a recursive form from that. So f of 6 is equal to f of 5 plus 11.
Okay.
F of 5 is equal to f of 4 plus what? Plus 9. F of 4 is equal to f of 3 plus 7.
Plus 1.
So how can I write 11 in terms of 6?
2x minus 1.
11 in terms of 6
Times 2 minus 1.
It's 2 times 6 minus 1, right? So let's write this as f of 5 plus 2 times 6 minus 1. And we're going to hope that each of these formulas has whatever x is on the left, we find that in the formula on the right. Then we can write a formula in general. So this is f of 4 plus 2 times 5 minus 1, which is making me happy. That's the same formula there. And this is f of 3 plus 2 times 4 minus 1. If I go back and do f of 3, that's equal to f of 2 plus 5, which is equal to f of 2 plus 2 times 3 minus 1, right? We can see patterns in different ways. This is the one I saw first. So now if I want to write a formula for f of n or f of x, whatever I want to write, that's going to be f of n minus 1 plus 2 times n minus 1, and then minus 1 from that. And I just guessed from looking at the form of all of these.
That n minus 1 should just be n.
Should be n. Okay. Just n. So f of n is equal to f of n minus 1 plus 2n minus 1. Okay, we just figured that out from the table. And we could prove that by induction if we wanted to. But let me also show you the cheap method. Okay, so say you look at this table and you're like, I don't know how to do alternating, getting odd numbers added to this thing, or my brain is just fried and I just don't have time to do this like this. Okay, you can also use the formula to figure out a definition. So you have to write in a closed form in a recursive form, your goal is to get a basis and to get a recursive step that gives f of x in terms of a previous value. But our recursive formula tells us what the previous values are, right? Our closed form, tells us what the previous values are. So f of x minus 1 is equal to what? Using my closed form is what?
X minus 1 squared.
X minus 1, quantity squared, plus 1.
Yeah.
That's just using my closed form definition. So this is the cheap trick. I'm going to subtract these two equations. I'm going to subtract the second one from the first one. That means subtract the left-hand sides and subtract the right-hand sides. And I'm going to get f of x and f of x minus 1 into the same equation. And then I'll solve for f of x, and I'll have a recursive step. And I didn't have to make a table, and I didn't have to look at consecutive values. I get the difference between consecutive values just by using the formula. So on the left-hand side, we get f of x minus f of x minus 1 is equal to x squared plus 1, and then subtract all this other stuff, x minus 1 squared. So we're going to subtract that. I'll just put a plus up there and subtract each of these things. So that's my first pass at my recursive step. I solve for f of x. That just means I have to add f of x minus 1 to both sides. I'll go ahead and put it at the front. Then I copy all the other terms over. Now, if I want to go back and check this with my table, I should combine these x squared terms and things, right? I don't technically have to. This formula will work. As long as I did my subtraction right for my left and right hand sides, this is definitely going to work, whether I finish doing the algebra or not. So what's left for giving a recursive definition here? I have to have a basis. So I just have to put f of 0 or some other value that I choose. That's 0 squared plus 1, so that's equal to 1. So if you're doing a test and it says, for the following closed form, give a recursive definition, find what f of x minus 1 is, subtract the two equations, solve for f of x. You've got a recursive step there, and you don't have to try to find a pattern under stress. Finding patterns under stress is a lot harder than finding them under no stress. As you start saying, there's no pattern at all, I can't see anything in that. Okay, but doing algebra under stress isn't half as bad, and depending on who you are. So if we were to multiply this out, we'll just double check it with what we had before. It doesn't hurt to double check, especially if you have extra time on the test.
That's 2x minus 1.
Then if we multiply, we can subtract. If we multiply x minus 1 out, we get x squared minus 2x plus 1. And then we subtract 1 from all that. That's equal to f of x minus 1 plus x squared plus 1 minus x squared plus 2x minus 1 minus 1. So notice I'm not skipping any steps here. If I'm going to do some hairy algebra like this, I'm not going to skip steps. My x squareds cancel.
Yes.
That plus 1 and minus 1 can cancel. So this is plus 2x minus 1. Makes me feel good because that's what we got before from our table. Okay, so it won't hurt for you to try both of these methods whenever you have a closed form. When you're doing your homework and you need to find a recursive form, you can try both ways and make sure that you can do it both ways and double check your answer. So for a lot of the homework in this class, you should be able to feel like you know whether your answer is correct before you turn it in. Okay, so can someone tell me again what the cheat method was? If you have to find a recursion based on a closed form, what do you do?
Subtract f of x minus 1 from f of x.
The very first step is to use the closed form to write the previous term.
Okay.
Right? So I write the previous term. The next thing is I subtract the left-hand sides and the right-hand sides, and I get a new equation that has both f of x and f of x minus 1 in it. And then I solve for f of x. So then I have recursive step, and I just have one thing left, and that is to get the basis. So you have a nice procedure for doing that too. So what's the point of doing this? Suppose that you had something that was really difficult to calculate in the closed form. Like say you were writing a simple program and you didn't know how to calculate sines, and there was no built-in function in your language to do it. If a recursive formula somehow took out those hairy computations, you would want to do it recursively instead. So you can calculate exponents and lots of things you do with summations. Those are recursions. Summations are recursions, recursive definitions. If you think about it, you can see that summations are just like recursive definitions. And sometimes writing a recursion is a lot simpler than using a closed form, where you can't do the calculation using the tools that you have. So recursion can be very good for you when you're programming. But if you just want to sit there with a calculator, and it's a scientific calculator with everything on it, then you might want to take a recursion and turn it into a closed form. So it's good to be able to go back from one to another. Also, you also might need to know what kind of values you have in a recursion. Like we said, we also are going to use, we're going to be measuring how long algorithms take. Not necessarily in this class, but later you will. In your data structures class, you'll be measuring how long it takes, an algorithm takes, and you'll be doing that with recursions. So you're going to you'll have recursive formulas for how long a recursive algorithm takes, and then you'll have to find a closed form for that so you know how long it takes. So we're going to be going back and forth, and lots in computer science, going back and forth between recursive formulas and closed form formulas. So let's talk about a method for finding closed form when we have linear homogeneous recursions. And this is in packet 3.2, which is going to be up tomorrow. And this is really detailed in packet 3.2, so don't worry too much if you don't get the details. Right here, you can print it out tomorrow. Take a look at it. But homogeneous means it has the right form. Everything looks the same. So we're going to have a formula for f or some other recursive sequence. It's going to be some constant times previous values. It's going to be sums of constants times previous values of the function. You could have more than two, but in this class we're just going to solve ones with two terms because I don't expect you to do anything with recursions that are looking back more than two terms, at least not for linear homogeneous ones where we're going to solve for them. And you'll see why, because we're going to end up solving for roots of quadratic equations, and I don't know many people who want to find cubic roots of anything, at least not on a test. Okay, so linear homogeneous means these are the only kind of terms I get to have. It's a linear combination of previous values of f. That's what linear homogeneous means. Linear means it's constants times previous values, and homogeneous means all of the terms look the same. Okay, so we also have to have a basis here. What?
Linear meaning there's no exponents other than 1.
Exactly, so we don't have any f squareds or anything. Okay, so we have to have a basis. Let's just leave out this plus dot 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 here because we're only going to talk about ones that look back at most two. We have to have a basis of two things. So we'll just call that B1 and B2. Just to remind you that if you have this kind of definition, you definitely have to have a basis also. So we'll do some examples, and then I'll give you the rules for doing it because I don't want to give you the rules before we do an example.
That way it's a surprise. That way it's a surprise.
That way it's a surprise.
How are we going to catch you if you're wrong, though?
It's all right. I won't mess up. I only mess up when I'm doing addition and subtraction.
Sure you do. That's just only when we catch you.
All right. You only catch me when I'm doing. Okay, fine. You can print the packet, and you can correct me next time if I make some mistakes, but I'll probably be fine. Okay, so let's say f of 0 equals 1. Now, actually, let's do... No, let's make it nice. F of 0 equals 1, f of 1 equals 3, and we'll say that f of x is equal to 2 times f of x minus 1 plus f of x minus 2.
How is that related to the B1 and B2, or they are two different things?
Basis values. It's not... I have to have two basis values.
Okay.
That's all. B1 is 1 and B2 is 3.
Okay,
We don't need to know that right now. We'll go back later and give everything letters and all that good stuff. Okay, we're going to solve this problem. Very first step is I'm going to make a guess. And I'm just going to tell you what the guess is, but I'm also going to tell you why. What kinds of formulas did we have when we had something just like that? When we had f of x equals twice the previous term? What kind of formula was the closed form?
Times
Power
x to
substitution.
x.
It was a power, 2 to the x. Remember those? So we're going to guess that the closed form has a power in it. So we're going to guess that f of x is really equal to some constant times a to the x. We don't know what a is. We don't know what the constant is. But we're going to guess. All right, so now we're going to plug this in. So if f of x equals that, then f of x is equal to x minus 1 is equal to c times a to the x minus 1, and f of x minus 2 is equal to c times a to the x minus 2. Right? We just use the same formula. So this first one is a guess, and the other one's just using that same formula for all the terms that we see in our recursive definition. then we're going to plug those in and try to figure out what C and A are. So we're going to plug all these back in to the recursive step. So f of x is c a to the x. We have a 2 times c a to the x minus 1. And then we add c a to the x minus 2. Now the c can be divided out of everything, right? So we're not going to be able to find it from that. But we can find a from this. This is one equation with one unknown. We can divide all the terms by a to the x minus 2. That's the smallest power of a that's in here. So if I divide everything a to the x minus 2, I should get this as reduced as I possibly can. When I divide powers, I subtract the powers. So if I have the same base, I subtract the powers. The top one subtracts the bottom one. So this is going to be a to the what? The last term will be just a to the 0, because x minus 2 minus x minus 2 is 0. The difference between x minus 1 and x minus 2 is just 1. X minus 1 is 1 larger than that, so this is a to the 1. I leave the 2 out front. And the left-hand side is x minus 2. That's a difference of 2, so the left-hand side is a squared. So that's a quadratic equation. If I get it in standard form, I can use the quadratic formula to figure out what a is. And I'll remind you what the quadratic formula is. So our very next step is to solve for 0 on one side. So we get a squared minus 2a, and a to the 0 is just 1. So we subtract 1. That's equal to 0. This is called the characteristic equation. And every time we see a linear homogeneous recursion, we're going to find the characteristic equation. And all of them are going to be squareds if the sequence looks back 2 steps. Because if we always substitute in ax to the n, cax, we're going to divide out a to the x minus 2 if we have 2 terms in our recursion, and we'll get a power of 2 in there. So it's going to be quadratic every time we look back 2. If we look back 1, what would it be like? It would just be like 2a minus 1 if we just look back 1 term or something like that. Okay? So it would be just a power of 1 if we only had 1 previous term. All right, now we're going to use the quadratic equation to figure out, quadratic formula to figure out what a is. So what's the quadratic formula? Anybody remember?
Yes.
A squared over something.
So first, the standard form looks like this. ax squared plus bx plus c equals 0. That's the standard form, right?
Okay. Yeah.
So using the standard form, if I want to find what x is, then x equals minus b
Plus or minus
B squared
b squared
plus 4ac
4ac over
2a.
2a.
There's the formula. X is equal to minus b plus or minus square root of b squared minus 4ac all over 2a. And I apologize for using x before in the powers, and now I'm using x in the base. And we're really going to find a. Little a. So our little a is equal to, so in this equation, the capital A is equal to 1, capital B is equal to minus 2, and capital C is equal to minus 1. So little a is equal to 2 plus or minus the square root of 4 minus 4 times 1 times minus 1 all over 2 times 1. So if I'm trying to figure out this is 4 minus 4 times minus 1. So that's going to be 4 plus 4 all over 2. That's equal to 2 plus or minus the square root of 8 over 2, which is equal to 2 plus or minus the square root of 2 times the square root of 2 over 2. And then I can cross the 2's out and get that that's equal to 1 plus or minus the square root of 2. And I apologize for having a hairy one on the first example, having square roots in it. That's the hardest part about doing these, is that it has square roots in some of the answers.
How do you know to make a good guess? I mean, there we'd worked some equations before where we knew that we were probably going to get a power, but how do you know what guess to make? Just
Well, in this case, we guessed that we were going to get a power because we had a linear homogeneous form.
Right.
And then we're going to check it later.
Okay.
So now I've got that I have two roots. I guessed that I just had one. I had a to the x. But I don't. I have two values. So I'm actually going to have to revise my guess. We're just going to have to do that. So we realized that we didn't have just one root. We have two roots. So we're going to go fix our guess and say that f of x must have been a sum of two powers instead of just one power. So if we look back at what we guessed that we had c times a to the x. I'm going to have to fix that and say it must be some c1 a1 to the x plus c2 a2 to the x. So we'll write that down. Because I had two roots. Anytime you have a characteristic equation, you're going to have two roots, you're going to have to fix your guess. However many roots you have to fix your guess to be a linear combination of all of those roots. If you have the same root, we have to do something different. So I'll do that case also. Okay, because if I have the same root and I try to have it a linear combination, if I do c1 a1 to the x plus c2 a2 to the x, but a1 and a2 are the same, that's really the same as a constant times a to the x. I'll show you that in a minute. You don't have to do it in your head. Okay? So we now know that we have two roots, so we have to say f of x must be a linear combination of a constant, c1, times the first root to the x, plus a constant times the second root to the x. Okay, so we said that one of our roots is r1, we'll just say is 1 plus the square root of 2, and r2 is 1 minus the square root of 2. So if I plug that into my formula, then f of x is equal to c1 times 1 plus the square root of 2 to the x, plus c2 times 1 minus the square root of 2 to the x. Now I have two unknowns. And how many equations do you need to find two unknowns? I don't know what C1 and C2 are, but I need to know what they are. I need two equations to find two unknowns. So what do you think I might be able to use? I could use the basis, right? Because I know f of 0 and I know f of 1. F of 0 was equal to 1 and f of 1 was equal to 3, if you remember. Even if you don't, that's what it was equal to. So we're going to use this closed form formula. So in terms of this formula, this is going to be c1 times root 1 to the 0, right? So I'm going to use this formula because I don't want to write my square roots too often. Then I'll do the algebra and then I'll plug them back in at the end. Okay, so this is c1 r1 to the 0 plus c2 r1 to the 0. This is equal to c1 r1 to the 1 plus r2 to the 1. Just using my formula, closed form formula, based on R1 and R2. But anything to the 0 is equal to what? 1. So these I can cross out. So 1 is equal to C1 plus C2. And 3 is equal to C1 R1 plus C2 R2. It looks a lot better and easier to digest. So now we have to solve for C1, and then we'll plug in that value for C1 into the other equation. So from here, C1 is equal to 1 minus C2, and we can plug that into the second equation. We get 3 equals 1 minus C2 times R1 plus C2 times R2. My next step is to find find C2, right? In terms of R1 and R2. Because C1 and C2 are the numbers I want to find. So if I find C2 in this equation, I'll be able to plug it back into C1. Can anybody nod and let me know that they're okay with where I am? Are we okay? Have any questions?
Right now it's just algebra.
We're just doing algebra. Okay, so even if you don't get it right now, you can go home and do it because this is not terrible algebra to do. So if I want to solve for C2, I need to multiply this out. I get R1 minus C2 R1 plus C2 R2. I'm going to subtract R1 from both sides and factor out a C2 on this right-hand side. It's minus R1 plus R2. So then C2 is equal to, if I divide both sides by that term, I'll get 3 minus R1 all over R2 minus R1. Because I have a minus R1 plus R2. It's a little easier to read if I reverse the order. So then if I went and plugged those back in, I could get C2. Well, I would get, if I plugged in R1 and R2, I'd get C2, and then I could plug it back in and get C1. And then I would have my closed form formula, right? Now in this case, I've done so much junk to get my closed form, I really want to do an induction, right? To be sure that my recursive formula and my closed form match. We're not going to do it on this problem because the square roots are a pain in the butt. And it would be hard for you to follow my algebra up here. So we'll do it for a simpler one, okay? All right, so here's an example of a recursion where we're going to go through the whole process. It's not going to be too bad. I'm going to use ends because in your notes there's ends, so I'll just use ends here. F of n is equal to 5 f of n minus 1 minus 6 f of n minus 2. Okay, the next thing that we have to do is get the characteristic equation, right? So at that point, I do f of n is equal to some constant times a to the n. So then I'm going to plug that back in. I get ca to the n equals 5 times ca to the n minus 1 minus 6 ca to n to the minus 2. So then I know that my last power is going to be 0, the next one's going to be 1, and the last one's going to be 2. Because I looked back 2. We know it's a quadratic equation. We can cross out all the c's. So we get a squared equals 5a minus 6. Then I have to get it in the standard form to find out what a is. So I get a squared minus 5a plus 6 equals 0. And then you don't have to use the quadratic formula if you can figure out how to factor something. This one is 2 and 3. A minus 2 times a minus 3 will give me this equation. And if you didn't see it, it's okay. You can always use the quadratic formula and it will tell you what those two numbers are. So then I have to fix my guess. F of n must be a constant times root 1 to the n plus another constant times root 2 to the n. And R1 is going to be 2 and R2 is going to be 3. So this is going to be C1 times 2 to the n plus C2 times 3 to the n. So now you have another clue. When I see a closed form that actually has just powers of n multiplied by constants, I have a really good feeling that it's going to be a recursive form that has 2 terms, that looks back 2 terms. And you can actually reverse the whole process we're doing so that if you find something that looks like this, you can actually get the recursive form. And we'll do that next, after we finish working through this. And then that'll be the end of class. Okay, so now we have to find C1 and C2. And remember that we had to use the basis because we needed two equations and there were two terms in their basis. Right? So we have f of n is C1 times 2 to the n plus C2 times 3 to the n. We have f of 0 is equal to 1, and we have f of 1 is equal to 2. So we use that.
Bless you.
So we get 1 is equal to C1 times 2 to the 0 plus C2 times 3 to the 0. We get 2 is equal to C1 times 2 to the 1 plus C2 times 3 to 1. So I'm just plugging in for the closed form for f of 0 and for f of 1. So 1 is equal to C1 plus C2. C1 equals 1 minus C2. 2 equals 2C1 plus 3C2. If I plug in for C1, I get 2 equals 2 times 1 minus C2 plus 3C2. Minus 2 plus 3 gives me just 1 C2. Subtract 2 from both sides. C2 equals 0. I probably messed up.
C2 is equal to 0. Wow.
2.
Well, that makes sense. C1 plus C2. So C1 is 1.
C1 is equal to 1. Well, we can check it out and see if that works. Okay? It could easily be that. So that means that C1 equals 1. And we'll go back and check it out. If C1 equals 1, then that means that f of n is just equal to 1 times 2 to the n.
How did you get that?
Which is 2 to the n.
I got that because we had our formula that f of n is equal to C1 times 2 to the n plus C2 times 3 to the n. And if C2 is equal to 0, then we just have the first term. And C1 was equal to 1. So I just plug back into that equation. So that's the whole point. When we find C1 and C2, we have to plug back in and write what f of n is. So now let's write our recursion and double check that this is true. So f of 0 was equal to 1. F of 1 was equal to 2. And f of n was equal to 5 f of n minus 1. Minus 6 f of n minus 2. So here's my proposed closed form, which is equal to just 2 to the n, and this is my recursive definition. So if we're going to prove that by induction, we assume that the recursive definition works, and we have to prove that the closed form works. Now this is where it gets a little bit tricky, because we have to change how we do our assume statement. The basis has to have how many points in it? Has to have 2. The assume statement always has to have as many points as the basis has. Okay, and I'm going to show you that. We're going to do that. That's because, remember that when we said we were proving a recursion from a closed form from a recursive definition, the very first step of the proof was to use the recursive definition to get f in terms of previous f's. If I use my recursive definition, it has to look back 2. So I have to have 2 assume statements with 2 closed forms. So the basis and the assume statement have to have the same number of things. So let's go ahead and start our inductive proof. We have the basis. F of 0 equals 1, and that is equal to 2 to the 0. F of 1 is 2, and that is equal to 2 to the 1. So the way I tell what I want in my assume statement is I look at my recursive definition, and I want a closed form for all the things that I underlined. All the previous f's, I want to know what those closed forms are, because in my proof, I'm going to write this formula out and want to do substitution on the right-hand side. So if I know what these are and put them in the assume statement, then it's really easy to do my proof. So I'm going to put f of n minus 1 here, and I'm going to use the closed form formula. So that's 2 to the n minus 1. And f of n minus 2 is equal to 2 to the n minus 2. And I have to prove that the left-hand side of my recursion, that's f of n, has the closed form also. So note again that these were just from the right-hand side of the recursive definition. So anytime you have to prove that a closed form and a recursion are equal, you can use the recursive definition to show you what you have to do in your assume statement. Okay, so we said that the first step was to write for f of n, we were going to use the recursive definition. So I just write that down. My next step was to do substitution. So it's 5 times 2 to the n minus 1 minus 6 times 2 to the n minus 2. My goal is to get that it's equal to 2 to the n. In order to combine these, I need both of them to have the same power of 2. So this 6 I'm going to break up into 3 times 2 times 2 to the n minus 2 because I know I can add the powers here for the 2 and get that that's 2 to the n minus 1. So that's the next thing I do. So I have 5 of the 2 to the n minus 1s in the first term, and I have 3 in the second term. So I can factor the 2 to the n minus 1 out of both of those terms, and I end up with 5 minus 3 if I factor those out. And that's 2 to the n minus 1 times the quantity 2, which is equal to 2 to the n. And that's what was in my proof statement. Do I have questions about this?
That's kind of cool. I see how you pulled the 2 out of the, I mean, you just basically took the derivative of the 2 to the n minus 2.
I didn't take any derivatives. There's no derivatives in here. What I did is I took 6 and I broke it into 3 times 2.
Right. Then where did that 2 go?
The 2 got combined with this 2. So 2 times 2 to the n minus 2 is 2 to the n minus 1 because that's 2 to the 1 times 2 to the n minus 2.
You're right.
Right. I just add the powers. Let me just do it so everybody can see. I skipped a step, so that's what we end up with. Okay. I have lots of practice with powers, and you may not, so you might have to see everything written out. Okay, so there is an outline of what you need to do when you have a linear homogeneous recursion. If you want to find the closed form, we get the characteristic equation, which ends up being a quadratic. We use the quadratic formula to find the roots. Then we have to modify our form, right? We have to have it be a linear combination of the roots. And then we prove it by induction. Okay, so just for a quick example, if I see let me use n's. I don't want to use x's. I want to use n's. I want to use n's because in mathematics, usually if you use an x, people think it's going to be real values, and if you use n's, people think it's going to be integers. And we're always using integers in this class. So if I forget, I'll try to go back to n's. So these are the same roots we had before, but it's not the same constants that we ended up with. Right, so the quadratic, if we went back and got the characteristic equation of this, it ought to be the same characteristic equation because these are the same roots. So if I see this, the first thing I do, if I have to find the recursive definition, is to find the basis, right? And I know if I have 2 roots, I'm going to need 2 basis points. Right, so I look at this and I say, this definitely looks like it was something from a linear homogeneous recursion. And it has 2 roots, so I need 2 basis points. So I'll go ahead and just fill out. F of 0 is equal to 3 to the 0 plus 2 to the 0. That's 1 plus 1, which is 2. F of 1 is 3 to the 1 plus 2 to the 1, which is equal to 5. So I have 2 basis points. And then I figure out what my characteristic equation must have been. These are my roots. So it must have been x minus 3 times n minus 3. That doesn't matter. Times n minus 2 equals 0. So if I multiply that out, I get n squared minus 5n plus 6 equals 0. And then I solve for n squared. And this must have been f of n, right? The squared term is that. Then I have 5 times f of n minus 1 minus 6 times f of n minus 2. So the squared term was the f of n. The next lowest term was f of n minus 1, and the next lowest was f of n minus 2. And I leave the constants out front the way they are. So here I have a recursive step and a basis. That means I'm done. If I don't have to prove it by induction, I finish the entire problem. And we have problems like this on the test every time. So I'll give you one of these. And you could either do it this way or you could use the cheat method. Right? I could write a formula for f of n minus 1 and then subtract the 2 formulas and find a basis, and I would have another recursive definition, which looks completely different. So there are many, many recursive definitions for the same closed form. So when you want to find a closed form, you hope that it's linear homogeneous because it's not too hard to find the closed form. If we did the cheat method on this one, let's see what it would look like. If we say f of n is equal to 3 to the n plus 2 to the n, then using the cheat method, we would figure out what f of n minus 1 is. It's 3 to the n minus 1 plus 2 to the n minus 1. And then I subtract the left-hand sides and right-hand sides. F of n minus f of n minus 1 is equal to 3 to the n plus 2 to the n minus 3 to the n minus 1 minus 2 to the n minus 1. Already it has too many powers in it for you to really think about what that means, right? But you solve for f of n. And you find a basis. Put a square around those and you have a recursive definition. So those are 2 totally different definitions that we get. Both of them neither of them require that much time. And both of them are valid answers. So I'm not going to require you to simplify this either. This is a formula, and it might be able to be simplified, but it might just be hairy. So don't, bust your butt doing some algebra because the computer can do it for you, right? So you can put this in Excel or whatever you want to use, and it would calculate all the values for you if you needed it to. Okay, are there questions?
How did you get n minus 3 and n minus 2?
N minus 3.
On the page before.
N minus 2. Oh, that's because the powers, the roots for the powers in this equation were 3 and 2. And if you remember our formula, whenever we're finding a closed form, we guess this formula. Right? That ends up being our guess all the time. That's root 1, that's root 2, where we have that's root 1, that's root 2, or whichever. It doesn't matter which one's which. So those were my roots 3 and 2, so it must have been n minus 3 times n minus 2 must have been the characteristic equation. And that's a place where I should have used an x, but that's fine. They're all the same. They're letters. They stand for variables. Okay, that's it for tonight. We'll see you next time. We're probably going to start on Big O next time.